Hello everyone. Today we're going to talk about the t-test, but in this case it's going to be for two independent sample means. We're going to talk about exactly what that means and how to apply it today. But note, everything that you've learned about the t-test, the initial design of it, why it was made, that applies here. We're just going to extend it to this other situation. So why are we actually going to use this? Well, first is it's going to be used for the same continuous dependent variable being compared across two independent or random samples. So you can think of this as between two groups where you have a treatment and control. You have quasi-experimental stuff where you are comparing individuals that play the piano and individuals that don't, and seeing what their cognitive scores are. So the question that you can really answer here is there a significant difference between the two group means? Now, other ways that you may have seen this in the wild is called an independent groups design, between subjects design, between groups design, randomized groups design. The key is for the t-test is that there's just two groups. When we talk about ANOVA, we're going to be extending this to more than two groups, but here it's just two. But all of those designs are names for this same overall approach. So like we've used before, we're going to use the same steps of a hypothesis test. So we state the hypotheses in null and alternative. And in this case, the null is that the difference between the means is 0, which can be written this way, or my favorite, this way. What it's saying is that in the population, there really is no difference between these two groups. The alternative is saying that they're not equal in some way. Again, my favorite's this one. Once we know what we're actually wanting to compare, the next step is selecting the statistical test and significance level. So generally, the alpha level is going to be 0.05. And again, like I mentioned before, we're going to go with two tails whenever applicable with a t-test. From there, we're going to select a random sample and collect data. We're then going to find the region of rejection, either based on the alpha and the number of tails or the t-test value. Ultimately, it's going to be based on that p-value. So in this case, we're going to use the t-statistic, and that is just the estimate minus the null hypothesized value divided by the standard error of the estimate. We're going to talk about exactly what that looks like in just a moment, but it's still going to be built just like we've been doing with the t-test before. So when it comes to actually calculating the test statistic, when it comes to the independent t-test, we have two general versions. The first one is called the separate variance t-test. The name helps a little bit. It's where the variances are not similar, and so we keep them separate. You can probably guess what the other one's going to do. It's when the variances are similar and we don't keep them separate. But this one, when we run this, note that this is the sample mean for group 1 and group 2. And then this is the null hypothesized difference in the means. And if you remember, that's just 0. So this drops out as just 0 here. So what you end up having is the difference in means divided by the variance of group 1 divided by the sample size of group 1, and the variance of group 2 divided by the sample size of group 2, all square rooted. What this is going to give us is an estimate of the standard error. Now, because we keep the variances separate, the degrees of freedom is less easy to define. But what we can say is that it's somewhere between the min of these two. So if we have a sample size of 10 and 15, we would have 10 minus 1 is the low end. And then the upper end would be both samples minus 2. The other version of the t-test is called the pooled variance t-test. This is where our variances are similar enough that we can just join them together. The top is exactly the same. The bottom is where we're going to now combine our variances into this pooled variance. And then we still account for the differences, the different sample sizes. The degrees of freedom for this one's a lot easier. It's just the sample sizes added together minus 2. And the pooled variance is just this. So it is essentially the sum of squares for group 1 plus the sum of squares for group 2 divided by the degrees of freedom, the sample size minus 2. So let's consider an example. This one, it's pretty small. We have a drug group and a placebo group. We have their scores up above. We're looking at the efficacy of a new antidepressant drug. And so we got 10 clinically depressed participants, and we're randomly assigning them to one of two groups. In order for this to totally work, what we're going to do is assume that prior to actually running the study, the experimenter confirmed that the level of depression in the two groups was equal. So we didn't see any meaningful differences between the two groups at the start. And then after 6 months, all participants are rated by a psychiatrist blind to the participant assignment on their level of depression, and that's the scores we're seeing above, where higher is more depressed, lower is less depressed. Now there's a couple ways that we can analyze this. First, just descriptively, this is just us putting in the data. So we have group 1 and group 2. But this isn't how we want our data generally to look. We don't want one variable to be the drug group and the other variable to be the placebo group. What we actually want it to look like is we want the group as a variable and their value, their score, to be another variable. So this is the same data in different formats. To get it here, one way is using the gather function. And so we're taking this into what is called long format. This is wide. And we're just essentially stacking them on top of each other. And then from there, we can get table 1 descriptives and even get a box plot. So the descriptives show us group 1 has 5, group 2 has 5, no surprise there. The value, which is our outcome, our depression level, group 1 has 2.8, group 2 has 7.8, and then here are our standard errors. We also can see the box plot here. Now note the box plots look kind of funny, but that's because we have a pretty small sample. So this slide shows how you actually run a t-test. First, we're going to start with the Levine's test. And note, value is our outcome, so that's their response to their depression scores essentially. And then this little thing here is called a tilde. And you have, so it's your outcome tilde grouping variable. Another way of thinking about that is dependent variable, independent variable. So this is saying we're comparing the value, their score, by the groups. And then the data equals dot means we're just grabbing this, whatever we piped in, and we're shoving it right there. And then importantly, we have center equals mean. Unfortunately, I forget that all the time, but that makes it so that this is actually the right test. And then we can look at actually what is happening with the homogeneity of variance here. Our p-value is 0.667. Now note, when we're doing the Levine's test of homogeneity of variance, the null hypothesis is that there's homogeneity. So if we don't reject the null, in other words, we retain it, then we do have homogeneity of variance. So this result right here is saying the variances are fairly equal enough. So when it actually comes to running the t-test, we tell the exact same thing here where we have value predicted by group, our data equals dot, and then we say var.equal equals true. That will give us a 2 samples t-test. When you see the 2 samples t-test, that means that the variances are equal. You'll see later on the Welch's 2 sample t-test, and that's when the variances are not equal. And here you can see the t statistic, your degrees of freedom, and the p-value. It also tells us the 95% confidence interval, which here is saying we're 95% confident that the true difference between the two means is between -10 and 0.87. The mean in group 1 is 2.8 and the mean in group 2 was 7.8. So the next question is, how do we actually put that into words? Note up here, I forgot to change this to be mean, and so the p-value is different. Just note to remember that. This is actually the right version. So using this output, we have after 6 months, the 5 participants taking the drug scored numerically lower on the depression scale compared to their 5 counterparts taking the placebo. To test the effectiveness of the drug at reducing depression, an independent samples t-test was performed. The distribution of depression scores were sufficiently normal for the purposes of conducting a t-test. In this one, we could compare the skew and kurtosis. I don't formally show you here, but we did in earlier ones. Additionally, the assumption of homogeneity of variances was tested and satisfied via the Levene's F-test. The independent samples t-test did not find a statistically significant effect. And lastly, there is no evidence that this drug reduces depression compared to placebo. So if you're putting into words, this is a great template to use. So when it comes to any statistical test, we have to remember there's going to be some assumptions. And these, for the independent samples t-test, is very similar to the one sample. The first one is both samples were drawn independently at random, at least as representative as possible. And when this isn't satisfied, there's nothing you really can do to fix a non-representative sample. And we can't test it. When this is totally violated, we can use often a paired samples t-test that we'll talk about more later on in the class. The second one is the variable has a normal distribution for both populations. It's not as important if the sample is really large because of the central limit theorem, but if the sample is far from normal and or has a really small n, you might want to consider transforming the variables to make them look more normal. To assess this assumption, we can look at plots. Personally, I love the QQ plot, but histograms and box plots are really great to understand how does it look like it's roughly normal. We also can look at skewness and kurtosis. We can look at the Shapiro-Wilks test. I don't use that one much, or the Kolmogorov-Smirnov test, which if you have a large N, you can use. I don't use either of those, but they're good to be aware of, that those are tests, and sometimes reviewers look for those. And then the third assumption is homogeneity of variance, and that's both populations have the same spread or variability. And that one we use the Levene's test, where the null is that there is homogeneity of variance. So you have these three. You have an independent random sample, the variable has a normal distribution, and you have homogeneity of variance. When it comes to random assignment, this is actually really important for a t-test to tell you anything meaningful about the differences between the groups. When you randomly assign to one of the groups, it means you're removing the experimenter biases. So you're just handing one of the groups off totally randomly to each person. However, it does not ensure equality of group characteristics. It's a great way to have the best chance of that, but it doesn't necessarily mean that it will. you still want to test to find out if other group characteristics look similar. Pre-test scores, anything that you think is related to the outcome, you'd want to see if those are similar across the groups, age, stuff like that. If you're doing an experiment, random assignment, and the manipulation of your IV, so in other words, you are, like this drug example that we gave, they're actually taking something that should change their scores. That is really helpful for using a t-test to talk about causality. And when you use that, you can use treatment versus control or two treatment groups. You also can use quasi-experimental designs with this, and that's either using randomization or manipulation. But the idea is still the same, where you aren't in full control over what group they're in or the manipulation they're getting. And then the last one is a non-experiment, and that's neither randomization or manipulation. You have no control over either. And that's when participants self-select or form naturally occurring groups. It's just what they do. Like the example I gave earlier, if someone's playing the piano or not, if they know how to play, it's usually a choice that they made or their family made, not one that you made as the researcher. The t-test can be used with all of these, but you can talk more about causation with experiment. You don't get to talk as much when it comes to quasi-experimental or non-experimental designs. So note, when violations of assumptions occur, when the groups are equal sizes, so your groups have the same number of people in them. One way to think about it is violations hurt less. So heterogeneity of variance, the p-value can be inaccurate a little bit. Non-normality, the p-value can be inaccurate a little bit again. However, if samples are highly skewed or are skewed in opposite directions, p-values can get very inaccurate. So non-normality, it's really important to look at, are they at least skewed in the same direction? Because that can be helpful. And if they aren't, then your p-values are probably going to be very problematic. So when it comes to having both problems, if your n is large, then p-values are still going to be inaccurate, but not by as much. If you have a small sample size, you're going to have a big problem with p-values. Notably, when these things happen, and it's becoming clear that the p-value is not going to be accurate. So when you have both of these occurring, and you know that your p-value is not going to be very accurate, or even just one or the other is occurring, you do have what are known as non-parametric tests that are very similar to a t-test, but don't rely on these assumptions. Generally, a t-test is best when the assumptions hold, but when they don't, going to a non-parametric version is really useful. In our in-class, we can talk about this a little bit more, but non-parametric tests, again, very similar to a t-test, just with different and fewer assumptions. Now, when you have unequal group sizes, violations hurt more. So when you have heterogeneity of variance, it's going to hurt you. There's going to be large effects, non-normality, large effects. Both, you're going to have huge effects. In other words, p-values can be very inaccurate when your groups are different sizes and you have violations of assumptions. And that is particularly true when your sample size is small. So often having a big sample size can help with a lot of things, but ultimately it doesn't save everything. Now, like I mentioned, when you have violation of normality or you have an ordinal dependent variable, you can use a two-sample Wilcoxon test. It's also called the Mann-Whitney U-test. You also can use sample reuse methods. These rely on empirical rather than theoretical probability distributions, so you can use bootstrapping, permutation, and randomization tests, or exact statistical methods, which I don't have a whole lot of practice with, but my coworker, Sarah Schwartz, has a lot of practice with. Ultimately, you are not out to dry when there are violations of the assumptions. It just means when you see those, you need to make a change and use a different approach. Now back to confidence intervals. When it comes to confidence intervals with independent samples t-tests, we're getting the 95% confidence interval for the difference between the means. What that means is our equation looks like this. It's the difference in the means plus or minus our critical t-value times our standard error. So if you're using the 95% confidence interval for your null hypothesis significance testing, if the CI does not contain 0, then you would reject the null. So let's go to another example. This one, we're looking at an industrial psychologist who is investigating the effects of different types of motivation on the performance of simulated clerical tasks. You have 10 participants in the individual motivation sample, and you have 12 participants in the group motivation sample. And they're both told different things. And then the number of tasks completed by each participant are shown. So if we bring that data in and we reorganize it like I showed in the previous example, we can get sample statistics out. So we have 10 in this group and 12 in this group. And we have 13.6 in the individual and 9.8 in the group. You can look at the box plots. These ones look a little bit more normal because of the larger sample size. And we can already get a hint for where differences might be between these two groups. Next step would be looking at the Levene's test, see if there's homogeneity of variance. In this case, we have a significant Levene's test. That means we reject the null of homogeneity. In other words, we have heterogeneity. And here, when you see Welch two-sample t-test, this is when your variances are not equal. It's no longer just the two-sample t-test, but the Welch version. And as you can see, when that happens, when variances are not equal, your degrees of freedom end up being not a whole number anymore. And there's a different calculation for it. But by saying var.equal equals false, we're adjusting for the fact that this is significant. So what we see is our t is 2.9 degrees of freedom and our p-value. In other words, it looks like there's a significant difference in the means here. We can see what the means are in our 95% confidence interval and the difference between the means. If we wanted to put this into words, we could say the number of tasks completed was numerically higher among the individually motivated group compared to the individuals being motivated by the groups. To test the difference in mean productivity, an independent samples t-test was performed. The distribution of depression scores were sufficiently normal for the purposes of conducting a t-test. Again, I didn't show all this, but we did that. Additionally, the assumption of homogeneity of variance was tested and rejected via the Levene's f-test. The independent sample's separate variances t-test found a statistically significant effect. Thus, individual motivation does result in a mean 3.85 additional tasks completed more compared to the group motivation. So hopefully those two examples were helpful to start to understand what the t-test is trying to do and what it can tell you and actually how to use it. Please post any questions you have on the discussion board and we can discuss them in class.